Let's move to the lecture 5. Numerical example, tangent vector space. This will be a different tangent vector space as you see. So, consider the Cartesian coordinates x1, x2. This is a point P, where the point P belongs to manifold and R2. You see, I have to have a point P, which is a label represented in Euclidean coordinates, Cartesian coordinates. So pick phi of lambda, lambda plus square root of 3, lambda plus 1. You see, this corresponds, is related to x1 of lambda and x2 of lambda. As I create this point here. Now let lambda is equal lambda p setting to 0. This leads to x1 of 0, square root of 3, x2 of 0 is 1. So this represents the point P, although is calculated using R2. Now this is a point P, okay? This is square root of 3 and 2. They are the Cartesian components. This belongs to R2, okay? Point P, x1, x2, the small x2, it has a label which corresponds to these points over here, which belongs to the Cartesian coordinates, square root of 3 and 1. So, look, I can't do any calculation, okay, is using x1 and x2 because they are just a label. I'm insisting for you just to clarify, okay, what is in general is written in the literature, okay? So that's important emphasis, okay? That I always brings you to this point over here, which belongs to R2. All the calculation must be done using capital X, okay? So now let the fantasy, I create a fantasy R and theta where x1, okay, is obtained by this relation R cosine and x2 R sine of theta. This R here, you can calculate R using x1 and x2. Just squaring, I would eliminate theta and get R2 is equal square root of 4, which is 2. On the other hand, the angle theta is arctan x2 of x1 is just sine divided by cosine, because you cancel R, this will be correspond to pi over 2. So that's point Q. Attention now, point Q, okay, coincides with point P, okay, but it represents in another Cartesian coordinates R2 that you call the fantasy. So note that Q is identical to P. Both belongs to M2 and both belong to R2. It's a little bit different because R2 for capital X1 and X2 is different from R2 using the fantasy. Okay, but they must represent the same point Q. Now observe that x1, okay, depends on R and theta, and x2 depends also on R and theta. Both belong to the Cartesian coordinates R2. Now, as I did before on lecture 3 and 4, okay, I want to calculate the differential at point P identical to Q. Again, I'm insisting, both belong to the manifold and belongs to the Cartesian coordinates. So that's differentiating dx1 with a function of r and theta. I just expand like that Likewise, the x2 I expand because x2 is also a function of r and theta. It's a fantasy. Now, both again are Pu identical to Q. Now, let's continue. Okay? Now, I just substitute. You see, quite easy. You see, the expression for x1 I derive with respect to r. Okay? This leads to cosine of theta. Okay? Likewise, partial derivative of x1 with respect to theta, this leads to sine of theta, d theta. So then I substitute, attention now, I substitute the point P, okay, just to calculate the x1 here. Okay, if I substitute point P, which I already have, okay, the point P, okay, I substitute over here, then I will get square root of 3 divided by 2 dr minus d theta. Okay, because r here is 2 and theta is pi over 6. So sine of pi over 6 is 1/2. So then I will get dr and d theta. Attention now, dx1 is called the one form, okay, the one which belongs to the cotangent vector space. That's important consideration here. Likewise, dx2, just clearly, I take the partial derivative with respect to r and respect to theta. This leads to sine and r cosine, okay, dr and d theta. Then I substitute at the point P, then I'll get minus 1/2 dr plus the 2 cancel over here, then I'll have square root of 3 d theta. Then I can write in terms of matrix, okay? This is 2 by 1, this is 2 by 2, this is 2 by 1 matrix. I just, from here, I just copy from here and check if I wrote correctly, you see? It's quite easy. So these are the basis vectors, okay, belongs, attention now, to the fantasy at point P, attention now. Everything here I'm doing here, I'm calculate at P, okay? That's the point P. Basis vector belong to this case, the tangent vector space, okay? Now, I move to the tangent vector space at PQ. Now I will obtain the tangent vector space. Consider the curve R is equal to, you see, I'm fixing r is equal to, and obviously dr will be 0. If r is constant, dr is 0. So note that for r is equal to, theta varies, okay, from 0 to 2 pi. Then this leads to, or recall in the literature, by tangent bundle. You see, many points over here, okay, that's this manifold, okay? These points over here, which each one I can obtain separately. Attention now, I can obtain separate its corresponding tangent vector. Okay, that's important here. But now I'm fixing. Okay, my objective is to concentrate on point P, which I already have the coordinates, see? So this, for if theta is pi over 6 and r is equal to, I can plot x1 and x2 as a function of these fantasy coordinates, see? So this I can plug over here. Attention, dr is equal to 0 because I'm working on a circle, okay, which r is equal to 0. I just copy, you see, I make dr is equal to 0, 0 here, and then I obtain dx1 and dx2, okay? Just canceling where dr is equal to 0. So I can obtain this differential over here. It's quite easy. Now we can see that I have this case, the tangent, the tangent vector, okay, that you live on this straight line. I want the equation of this straight line. From calculus, you see, easy. We can obtain this, the angular coefficient, okay, is the dx2 divided by dx1. This is minus square root of 3, which I already calculated. So x2 m x1 plus k, which m already calculated is minus square root of 3 x1 plus k. Now I need to obtain k, so I substitute the point at P, okay, to calculate k. Substituting the coordinates x1 square root of 3, x2 is equal 1, then I substitute and obtain this this called linear coefficient k. So then I have the equation of the straight line, which is the tangent plane, in this case, okay, on M, okay. This, attention now, okay, this is not a plane, this is a tangent vector space. Plane we derived on the previous lecture, okay, because the manifold was M3. Now the manifold is M2. See, so in this case the vector space is not a plane. The vector space is a straight line. Attention now, working on R4, okay, the vector space, the tangent vector space, will be, for instance, a sphere, okay, because when you work on R4, okay, just to decrease by 1 this vector space. Okay? Now the manifold, the dimension is 2, so the tangent vector space is not a plane, it will be a straight line. So then I obtain the